اوكي طيب so gng and today شباب please turn off your mics يعني حمد okay good so today we'll do the birthday problem. We'll do introduction to probability and the axioms of probability. And of course, we will have quiz 1 at the end of the class. Okay. So let's start with the birthday problem. And the problem in our class, we have I think we have 42 students, and we want to find what is the chance, sorry, what is the chance that at least we have 2 students with the same birth date. So this is the problem that we want to solve. So let's start with some questions. The first one is, and I mentioned this early on when we started talking about the counting techniques. Counting techniques are usually telling us how many elements I have in the so how many elements we have space of this experiment. And this is what we call the cardinality or size of S. So we denote it as like this absolute value of S. So what's the sample space of this experiment? What are the different, remember, and even today in the quiz, I will ask you to write down the sample space of a certain experiment. So what's the sample space of this experiment that we are talking about? So,
Doctor?
yes.
I think from 1 to 22.
For the question, I think there's 42, right? For the question written, the answer is 42, right? Because there's 42 students.
No.
I think it's
I'm
all
telling you.
day.
316.
But doctor, you
One
asked
second,
how many
one second.
elements? Not
second.
what are sample spaces.
1 second. Here I'm asking for the sample space of the birth date of 42 students in the class.
Doctor, all the years from 90 to 2000 at least. So 365
No.
times.
Doctor, 3 elements.
Shabab, I'm not concerned about with the okay. We celebrate, yani people. I don't celebrate my birthday, but those who celebrate their birthday, regardless of the year. One was born in 92, one was born in 95. If both were born on January 1st, they will celebrate on the same day, right?
Yes.
So I'm not talking about
165, Doctor.
165.
I'm not talking about what year. I'm talking about the birth date, month and day. This is the first thing. The second thing, we have 42 students. What will be the elements of the sample space of their birthday? So the first element of the sample space, that all 42 students are born on January 1st, right? Or this can be an option, right? Can be an outcome.
So the day of
Or-
the month.
Yes, the day of the month, and we have to count all options. So the sample space, the first element, it's
31.
January 1st, January 1st, January 1st, all the way to students number 42. So this is one element. Then the second element in the sample space, the first student will be January 2, and then the second is January 1, all the way to January 1. Then you have to count all options, right? So every time you change the birth date of the first one, and you keep doing this. Once the first student reaches January 31st, you go February all the way until the first student reaches December 31st. And then you start with the second student, and then with the third student, all the way to 42. So this is a huge number. So you keep doing this until you reach December 31st for the first student, December 31st for the second student, all the way to December 31st for the last student. And this will be your sample space. Aziz, go ahead.
Can you repeat, Doctor, please?
Doctor, I have a question.
But let me repeat, and then you ask your question. So the problem is we want to go to a class of 42 students and ask each student, what's your birth date? What will be the possible answers? This is the sample space, right? You ask 42 students, what's your birthday? What year, what month, and what day of the month? And you write this down. What will be the possible answers?
365 power 42.
Yes, that's what we will. But if I ask you to write it down, it's a huge number, right? You have to count all possibilities. So you start from January 1st, all of them, until you reach December 31st for all of them. And in between, you have all combinations, all possible dates of the year, which are 365 days of the year.
So now, Doctor, December 31 for the whole student, right? And
until you reach that one,
yeah. Okay.
And in between, you will have all combinations. So someone had questions? Okay. So S, the size of S, yes.
But I'm a bit confused. In order to calculate the possible combinations of their birthday, here you just started for you were changing the date, the birthday of the first student, and the rest were constant. But it's possible that. But it's possible that.
Yes, go ahead.
It's possible that. For example, the first student could be in January the 2nd, and for example, and the fourth student will be in January the 2nd also, and the rest and so on.
Yes, if you do this all, if you write this all, you will pass with that. So I started with the first student until you reach the first student,
yes,
December
yes, yes.
31st, and then you go to the
Now I
second,
get
and then you go to, so you get
Thank you.
all possibilities. So that's why when you want to count how many you will have, so you'll have 365 options for the first student, and then 365 options for the second student, and 365 ways for the third students, all the way 365 days for the 42nd student. So this is first student, this is second student, all the way this is 42nd student.
So it's
So this-
365 power 42.
Yes. So
Yeah,
this is
thank
how
you.
many you have in your sample space. Right. Next, I will ask this question. What's the size? What is the size or cardinality of the event that all birthdays are different? And call this so if I want all birthdays to be different, what's the size of A? So if you want to follow the same
42?
procedure, no, it's much higher. So now the only difference compared to the sample space is that assume that you are doing this in sequence. So how many options I have for the first student? 365 ways. But when you go to the second student,
Minus
you have
1.
364 minus 1, right? And the third student,
365.
365i.
Until
Factorial.
you
until you reach
Factorial,
what?
doctor.
365 minus 42.
Till you reach 1.
Minus
42.
41, doctor.
41. Why 41?
Because we already have
Because
365.
yeah, because this is the first
yeah.
student. This is the second. So the second is minus 1, right? It's 365 minus 1. Third is 365 minus 2. So it's always one less. So the 32nd student it's 41. So which is equivalent to what? To 365 factorial divided by what?
42.
42 factorial, right?
Yes.
Which is what? It's like in factorial over what? Over r factorial, right? So it's or leave it as is. It's n factorial over r factorial. You can write it this way.
Doctor,
Yes.
this is a general formula, right, for any event, n factorial over r factorial?
No, I'm just trying to write it in a nice way.
Sorry, doctor, but why did we reach
So this is no. 1 second. So this is not r. It's n minus r factorial, right? Not 42 factorial. This is
365 minus 40.
yeah. So this is 365 minus 42 factorial, which is what?
41, Doctor.
Factorial. So this is, if you do this factorial, so what's this number?
323.
20. This is 324, right?
Yes.
So this is, if you want to write the one, it's not to get confused. I don't want you to confuse me even. So this is 365 times 364 all the way times 324. So if again, if we want to add by colors, so this is 340, 23, 322 all the way to 1. And then at the bottom, I will 323, 322 all the way to 1. So this is 365 factorial over 323 factorial. And 323 factorial is what? Is 365 minus 42, right? Factorial.
Amazing,
You
Doctor.
agree?
Amazing. Amazing. Yes, perfect. Thank you.
Yeah, now it makes sense.
So, and this is what we did last time. Which is the permutations. It's like you take a subset. You have a set of 365 days of the year, right? And you take a subset of 42 birth date, and you distribute it among the students. You want to find all the combinations among the students, where order matters here. Why order matters? Because if Ali is January 1st and Muhammad is March 1st, it's different than when Muhammad is when Ali is March 1st and Muhammad, and it's the other way around. This is a different event, so order matters. So that's permutations.
Professor, I have a question.
Sure.
Shouldn't it be 366?
No, we said, yeah, I did not write the assumption that we assume we have a simple year. We assume
okay.
nobody was born on, okay, let me write, probably I should have written this. So assuming simple years, no one is born on February 29th, okay? So yes, thank you. We should have stated that. Fine. So the last thing we want to say is, now going back to our original question, I want the probability that I have multiple students with the same birth date. What's that probability?
We just start counting from 364.
365 power 42 minus the A. Why we got it now?
Yes, but we are interested, and let me state why. But we are interested in the event of repeated birthday or multiple birthday, or at least 2 students with same birthday. So this is exactly the complement of event A that we found, right? Because here, what we found here was the event that no 2 students have the same birthday. So all the other events, or the complement of this event is that at least 2 students have the same event. So our what we are asking for, so A bar is the event of interest to us, and A bar is just what? It's just S minus
Doctor, I
A.
have a question.
Yeah, let me just finish this. So this is just 365 to the 42 minus
365i.
P 365 42. Yes, go ahead with your question. So this is where this is A that we found out. Yes,
Doctor,
question?
and the first one, we found if the possibility if we're gonna have a student of 42, all of them have the same birthday. The first
No,
question.
this one.
No, not this one. The previous one.
The previous one, the one that. Which one? This P365 over.
That's all the
42.
The 365 to the power 42. That was the possibility.
This is the whole sample space. This is the whole sample space. It has all possibilities.
A combination, 2 students or 4 have the same birthday or whatever, right?
Yes,
and
everything. Not having the same birthday, all having the same birthday.
And in this question, we are finding what? And in this, the last part, what are we trying to find?
So the first step was, let's go back again. So the first step, we found the size of the whole sample space, all events. This is all events. Okay, all possibilities of all birthday. Yani part of this, that all of you are born on January 1st. All of you are born on January 2nd. All of you have different birthdays for the different combiners. So the sample space have everything. Then we moved and calculated how many possibilities to have different birthdays. That all of you will have different birthdays. How many possibilities? It's still a very large number. Then we said, then what's the probability of having at least 2 students having the same birth date? And this is which is the complement of the event. So if you have an event that no one has the same birthday, what's the complement of that? Complement of that 2 or more students having the same birth date. And that's why we can find the cardinality or the size of this event by subtracting the size of A from the size of the sample space. And if one of you can calculate this and bring it to us next time, you will find out that the chances, if we calculate the chance of having 2 of you with the same birthday is very high. More than like 85% or 90%. I do not have the exact number. So one of you, please calculate. If you want to calculate the exact probability.
The problem is 365 to the power 42. The calculator cannot find the answer.
Yeah, so that's why you can calculate the probability instead, which is this. You do some things by hand first, and then 42. Sorry, not why I'm writing 45.
It's around 4.1 times 10 raised to 107.
No, calculate this. This will be around 0.8, 0.85, 0.9. I don't know. Because this is 1. The first part is 1 minus permutation of 365 over 42 divided by 365 to the 42. Just calculate this, someone, and you can revert back to us next time. Okay. Done with birthdays. And happy birthday for those who are celebrating their birthday today. I can't participate in such official one, not official, so I will mess up the whole calculation. But let's go to the second topic of today, which is introduction to probability. Let me circle this in red. So what's probability? Probability is the likelihood or chance that a particular outcome or event from a random experiment takes place or occur. So this is what a rough definition of probability. When we say the probability of that event or probability of that outcome, we just talk about, we are estimating the chance that a particular outcome or a particular event is going to take place once we do the random experiment. Once we conduct the random experiment, we expect a certain event, and since it's random, which outcome will be, but what we can do is we can state the likelihood or state the chances that I will have this event or that event. So how can we come up with this number? That's what we going to say about types of probability. The first type is subjective probability. And subjective probability means that it's a way of assigning probability to reflect our belief based on studies, calculations, and so on. For example, forecast. Weather forecast, sometimes it says, okay, we have 50% chance of rain tomorrow, or 60% chance that we have wind from the north. How did they come up with this number? 50% or 60% or 20%? This is a number that's based on the movement of the winds, the air pressure, the weather in neighboring countries, and so on. So they do some calculations, some forecasts, and then based on their belief, they will come up with this number. So there are some activity behind the number, but This is the way we come up with this number. So this is one way of assigning probability. So here mark like 50% chance of rain. The other way of assigning numbers to probability is what we call the relative frequency probability. This type, it deals with the random experiments that you can repeat in the lab, or you can repeat yourself. So this is based on repeating an experiment, a random experiment, large, very large, or large, very large number of times, and then dividing the number of outcomes for a certain event by the total number of experiments, by the total number of repetitions. And a good example for this is what? Tossing a coin. Like 1,000 times.
Doctor?
And then, one second, and then dividing the number of times you get ahead by 1,000. This should give you a number close to 0.5. Like if you do 1,000 time tossing, probably you'll get like 510, 520, 470 heads out of those tosses. Okay, question?
Doctor, I have a small question regarding so this tossing coin is a random event, right? But
Yeah.
the definition of tossing a coin of a random event is that it should be done the same way, but should give different outcomes, right?
Yeah.
So, but if you do the tossing of coin in the same exact way, like you place it in the same place, you give the same force and the same distance from the ground.
Yeah, you still get, because you will not be able to do this perfectly. Try toss a coin many times and see.
No, if someone sets up a small machine or something which does it and with the same force and everything, even then it'll be random? It doesn't seem like.
If you can perfect everything, it will not be random, but you will not be able to perfect because the machine will can adjust to a certain accuracy again. The force up, right? But it will not unless you put this in an isolated room with no air pressure, and then you will assume that the gravity of the Earth is exactly the same, is not changing, which is not true. So there's a lot of imperfection in this, and the only way probably you will get this fully random if your machine has the ability to place the coin on its edge, and then it will throw it. Okay, because if everything is perfect, then if it's facing up, the head is facing up, probably you will get either head or tail. And so either you switch if everything is perfect. So you have, sorry, I think it's my iPad. You cannot see my screen, right? So if everything is perfect, when you repeat your experiment, you should switch between head and tail on top of the machine. Otherwise, it will not be a fair repetition of the experiment.
But the definition says that it should be if an event is repeated in the same exact way.
Yes.
In the same exact way, and it gives different outcomes, but it's not necessarily true. Like, do you see where I'm going? Like, if you do it the same exact way, it doesn't stay random anymore. It has to be done in a different way every time.
Yeah, I would say this is more of a philosophical argument than of what's in reality, because as we mentioned the first day of classes, all of this randomness is coming from imperfectness. So you cannot tell me that what if everything is perfect, will it still be random? No. If I know everything and I have everything perfect, there is no randomness in any experiment, in anything in this life, if we have everything is perfect. But we'll not be able, what I'm saying is, we'll not be able to have everything fully perfect, because even the gravity of the earth is not only controlled by us. We cannot control it. It's controlled by the movement, and where is the air to the sun and to the other planets, and they are all moving, even though the change in gravity is really little, but still we cannot control all the effects that will govern any random experiment that we have. Okay. Fine. So let's move on, because we have a quiz, and I have only a few minutes. 1 second, if you can give me 1 second. Let's have a note here. Which you probably know by now. If the sample space S consists in possible outcomes that are equally likely then the probability of each outcome is, and probably I use again, is 1 over n. And we have our famous examples for this. For example, tossing a coin. How many outcomes I have in tossing a coin? We have 2 outcomes, right? So the probability of head is 1 over n, which is 1 over 2. Probability of tail, again, is 1 over 2. In throwing a dice, we know that probability of 1 is the same as probability of 2, is the same as probability of 6, which is, every one of those is 1 over 6. And the birthday, if we take the birthday problem that we just solved, if I ask what is the probability that all students in our class are born. Sayed, please turn off your mic. Saeed or Sayed. Okay. What's the probability that all students in our class are born on, for example, April 20th? So this is a single outcome in the whole sample space. So the probability again is 1 over n, which is 1 over 365 to the power 42, which means 365 to the minus 42, which is very, very small number. Okay. And of course, again, I don't want to go back to the birthday problem, but there are many assumptions behind it. Assumptions that people do not control the birth date. I know now there are more control. People like to have birth on the New Year Eve or certain days of the year. But there are many assumptions that every day has the same probability. Okay. طيب. If we move on with our notations, we can say that for a discrete sample space, the probability of an event E, probability of E, is the sum of probabilities of all outcomes in E. What does this mean? For example, in throwing a dice, if we ask, what is the probability of getting an even number?
3 over 6.
So what's this event? Let's say event E. So in this case, yes, you're right. So it's 2, 4, 6, right? So what we are saying, probability of E equals probability of 2 plus probability of 4 plus probability of 6. So we add the probabilities of the outcomes inside that event, which is 1 over 6 plus 1 over 6 plus 1 over 6, which is 1/2. So if I have an event that is composed of few outcomes, then to find the overall probability of that event, we just add the probabilities of the outcomes inside that event. Okay, and now we come to the important part, which is the axioms of probability. Or the rules, or the most important rules of probability. And with that, let's say just again that probability is a number that is assigned to each member of a collection of events from a random experiment which satisfies the following. So we have three rules, or three main rules for probability, which we denote as axioms of probability. So the first rule is that each probability, each number that we assign to an event, so we can assign probabilities to outcomes, single outcomes. We can assign probabilities to collection of outcomes or events. And of course, we have the probability of the whole sample space. So what do you think the probability of the whole sample space? Anyone? What do you mean by the probability of the sample space? Means that the probability that when we run a random experiment, we get an outcome from the sample space. What's this probability?
It should be 100, right?
Should be 1, which is the ratio is 100, but in absolute sense, probability is 1. Is the maximum probability that we can assign is 1. So again, this means that when running a random experiment, we should get an outcome. So if you toss a coin, you'll get either a head or a tail. It's like I'm asking you, what's the probability that you will get a head or a tail when you toss a coin? For sure, you'll get a head or a tail. There's no, as we said, it's a fair coin, and it's assumed that it cannot stand on its edge. So the probability of the sample space is 1, because probability of sample space means the probability of adding the probabilities of each single event in that sample space. And if at any point you have a sample space and you try to calculate its probability and it was not 1, it means that you are missing some of the events or some of the outcomes from that sample space. Rule number 2, very important rule, which is the probability of any event should be between 0 and 1. And this is really, really important rule. And every time I teach this course, I warn students, when you are asked to find probabilities in homework, in an exam, in wherever, you should not get a number larger than 1, and you should not get a negative number. If you do your calculation and you get number larger than 1, and you couldn't find where the error is, you just write down probability should not be larger than 1, so I should have made a mistake in my calculation somewhere. This will save you some credits in the question. If you leave it, you find a probability of 2.5 or 3 or 10. It means that reflects to me that you do not understand the axioms of probability. Or if you get a negative probability, it's even worse. Negative probability does not have any meaning. So probability of any outcome or any event should be between 0 and 1. So be careful. Rule number 3, for two mutually exclusive events E1 and E2. Mutually exclusive means E1 intersects E2 is the empty set, right? So if we have this, then the probability that E1 union E2 is simply probability of E1 plus probability of of E2. So these are the three golden rules of probability. You can prove any other probability rule based on those three axioms of probability. So for example, let's do some examples. If you are asked to prove that probability of E bar equals 1 minus probability of E. How do you prove this? Using the axioms of probability. Let's start. We start with axiom number 3. Now we know that by definition, E intersects E bar is phi, right? The empty set, the complement, the event and its complement, they do not have anything in common. So by definition, then using rule 3 or axiom 3, probability of E union E bar, is probability of E plus probability of E prime. But we know that E union E bar is just probability of S. E union E bar is S by definition. So this probability of E plus probability of E bar. So this is by definition again. So now we know using rule number 1, probability of S is 1. So 1 equal probability of E plus probability of E prime. So which means that probability of E prime is just 1 minus probability of E, and you proved this relation. Also, you can prove, for example, if you are asked to prove that probability of the empty set is 0. So again, you can start. We know that S intersects phi is just the empty set, and then based on rule number 3, probability of S union phi equals probability of S plus probability of phi, and we know that this is just S, so this is probability of S equals probability of S plus probability of phi, so 1 equals 1 plus probability of phi, which means that probability of phi is just 0, and so on. You can do this for any other rule. Let me state one large.
The S intersection with the phi, is this by definition, or how do
by
you
definition? Yes,
know this?
yes, from the definition of the sample space and the empty set. Okay, by definition. The last rule I want to mention is, in general, for any two events, A and B, probability of A union B, if we don't know whether A and B are mutually exclusive or not, this equals probability of A plus probability of B minus probability of A intersect P. And I will not prove this using the axiom. You can just prove this using Venn diagram by intuition. So if this is A and this is B, then probability of A, we know that this is probability of A. And then if you know you want to do another color for probability of B. So if you add those, you see that this area, if we add PA plus BB, this area is counted twice, right? Then we subtract it so that it's added only one time. Okay. So I will stop at this point. So now what you need to do, you go to Blackboard. Let me enable the check-in quickly so that you can check in, and then we will move to the
Doctor,
yes.
regarding for the quiz, it will be multiple choice, right?
No, it's not multiple choice. I said you have two questions. One question is you will need to find the sample space, and the other question you need to write whether a certain
But will we scan
experiment that
because
no, you
last
don't
time
scan,
you
you
said
just enter, because you just type in your answer.
okay.
Okay, 1 second. I'm getting into Blackboard. I will enable your we have time, don't worry. So you are L02, right? Where's L02? Okay. And then attendance. Okay, please start checking in your attendance. Once you check in, go under assignments and you will find quiz 1. You started and start solving. So please check in first and then go to the quiz. And the quiz, you have to answer the first questions. Once you answer it, you can go to the second question. You cannot go back to the first question.
Doctor, just want to ask you a question.
Yes.
Like if there is something like for some people random.
I can't hear you well.
If there was something